Chapter 13, sound. We're going to talk about some properties of sound. So let's begin with a tuning fork. Here's an example. Here you see a drawing of a tuning fork. These straight parts of the tuning fork are called the tines. When you strike the tuning fork on a surface, they vibrate back and forth. Like you see, this red line here is vibrating back and forth. Let's see a tuning fork in action. Okay, so this red line here represents the tine of the tuning fork. As it vibrates back and forth, it compresses the air molecules, and as it moves backwards, it decompresses the air molecules. These are called compressions and rarefactions. And so the number of times that the tuning fork vibrates per second is the number of compressions that are formed each second as well. Remember how when we talked about interference patterns, we watched this little video here of an interference pattern. Well, we can see what an interference pattern looks like for a tuning fork with this animation right here. Right in here, you can see that we're looking down on top of the tuning fork. The two tines are vibrating back and forth. And around the space around the tuning fork, this interference pattern is created. So you can imagine if I were to walk around the tuning fork, I would be in these regions of the interference pattern, and you can see here, this is where constructive interference is occurring. Here, destructive interference is occurring. Constructive, destructive. And the way we can identify this with sound is the volume. Here, the volume will be higher. Here, the volume will be lower, higher, lower, and so on. So let's demonstrate this. But instead of walking around the tuning fork, I'm just going to take the tuning fork and rotate it. And listen to the volume, the changes in the volume as I do that. So the volume is represented by the amplitude of the wave. Here we have two representations of sound waves. This is what's really happening with the air down here, but that's so hard to draw. So instead we draw like these blue lines here where the compressions are represented by high pressure and the rarefactions are represented by low pressure. So high pressure, low pressure, high pressure, low pressure. And these two waves here are of different amplitudes. Different amplitude waves have different volumes. Down here is the actual sound wave. This top wave has higher amplitude because the density is higher. And here you can see the graph is higher, representing higher density. And down here, the density is not as great, so the amplitude is less. This wave is louder. This wave is not as loud. And then the frequency is represented by the pitch of the sound. Here you can see in 1 second, if you went through and counted these, you would count 25 waves. So that's 25 hertz. We say the frequency is 25 hertz. And down here you can see there are, if you went through and counted these, you would count 50 waves. So the frequency there is 50 hertz. And that frequency determines the pitch. Let's click on this tone generator here. So this website will allow us to enter in our frequency that we want, and we can hear what it sounds like. And I can choose notes on the scale. And you can see the frequency right here. And what you notice is when you double the frequency, here we've got 130.8. I doubled it to 261. doubled it to 523. You might recognize that. When you double the frequency, you go up by an octave. So our range of human hearing is from about 20 hertz up to about 20,000 hertz for good ears. Let's go back to the tone generator software. I don't know if you can hear that, but I know I can't. I can't hear it anymore after about 16,000 hertz. You can play with this if you want and see where you drop out. Older people tend to lose their hearing in the high frequencies as they age. Let me show you something. I actually went and had my ears tested, and here is a hearing test that I had. You can see that here's about normal hearing. When it got up to about 2,000 hertz, you could see my hearing, my ability to hear the sounds started to drop off. The lower these marks go on the chart, the louder they had to make the sound before I could hear it. And you can see at about 6,000, that's where my hearing is the worst. And in that range of frequencies, these are the letters or the sounds in speech and where they appear in the frequency range. So up here around 6,000, letters like F and TH and S, so F and Th and S. I have a hard time hearing those, and so it makes understanding words a little harder for me. These sounds in language are down in these lower frequencies, and so I don't have much trouble hearing those. Different frequencies of sound can be used to make images. You may have heard of ultrasound before. So instead of light, they send sound out and listen to the reflections of the sound, and from that, kind of like a bat can find things with echolocation, so too can we make images using sound waves. Let's see an example here with this video.
The heart of most ultrasound systems is a device called a transducer, which uses an array of piezoelectric crystals. A piezoelectric crystal vibrates when an electric signal is applied, producing high-frequency sound pressure waves, which we call ultrasound. More importantly, this type of crystal can also work in reverse. It can produce electrical signals when it detects high-frequency sound pressure waves. When a transducer directs ultrasound waves into the body, they pass right through the skin and into the internal anatomy. As the waves encounter tissues with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal. This happens more than 1,000 times a second. Returning echoes are converted to electric signals, which a computer converts into points of brightness on the image, corresponding to the anatomic position and the strength of the reflecting echoes. A medical transducer contains a large array of crystals, which allow it to make a series of image lines that, together, form a complete image frame, called a sonogram. In addition, all the crystals are repeatedly activated many times in such a way that a complete image frame is formed around 20 times per second, so that real-time motion is displayed in the ultrasound image.
So we said that sound causes things to vibrate, and here we see a sound wave traveling through the air. We call the air the medium. The stuff through which the sound is traveling is called the medium. Doesn't have to be air. But let's look at an example when the air is removed. Here is a poster that you can find in my classroom. It's from the movie Alien. The tagline for the movie, "In space, no one can hear you scream." Why is that? Let's check out this video.
If sound is vibration, Phil, how does it get from one place to another?
Mostly through the air, Jimmy. You see, the vibration of my voice box makes the air vibrate between us. Then when the air vibrates your eardrum, you hear what I'm saying.
Vibration of voice box.
You can prove that air carries sound by... But maybe you've seen a demonstration of a bell under a glass jar? With normal air inside the jar, you could hear the bell clearly. But when the vacuum pump drew the air out of the jar, there was nothing inside to carry the vibrations of the bell. Nothing until the air was let back into the jar.
And sound doesn't have to travel through the air. It could travel through water or the ground or all sorts of different media. So let's check out this video to show how the speed of sound is different depending on the media that it is traveling through.
If you don't believe that air vibrates, take a look at this. Sound waves can travel through solid things like wood as well. The particles in a solid are packed together far more tightly than air particles. What difference do you think this makes to the sounds you hear? Listening with a stethoscope can hurt. Does sound travel faster in the ground or through the air? And is the speed of sound ever as fast as the speed of light? To find out, you need to make a sound that can travel a long distance. 5 tons of plastic explosive should do the trick. How would you detect sound waves in the ground? Samantha's going to watch for the explosion, but she's wearing headphones so she can't hear it. Fung is going to listen for it, so he's wearing a blindfold. And Elizabeth's going to detect sound waves in the ground.
Ready?
Ready?
Ready.
So, who's going to be the first, second and third to detect the explosion? They were waiting to see the light, hear the sound, or feel the sound. Samantha was first because the light got to them before the sound. Elizabeth was next when she felt the sound coming through the ground. And Fung was last, when he heard the sound of the explosion coming through the air. The speed of sound in the air is 350 meters per second. At 5,000 meters per second, sound travels much faster through the ground. But light is much faster than any sound, at 300 million meters per second.
An interesting phenomena occurs when sound is being generated by a moving source. or whenever there's relative motion between the source of sound and the receiver of the sound. Here you can see a stationary sound source. Here's the source of the sound, and the sound travels away in all directions at the speed of sound. But what if the source is moving? Down here you can see as the source moves, in the time it takes between the generation of compressions, the location of the source has changed. So in the direction that the source is moving, the compressions are closer together, and behind the movement, the compressions are further apart. So an interesting thing happens. If you're standing over here, now those compressions pass by your ear at a different frequency. The time between the compressions is less. And if you were standing over here, the time between the compressions would be greater. So in other words, the frequency of the sound changes. And we know that frequency relates to pitch. Here's the diagram in the presentation that shows the compressions are closer together as the car approaches you. And if the car is moving away from you, the compressions are further apart. So the result is lower frequency equals lower pitch, and a longer wavelength, the distance between the compressions is greater. And over here, the frequency will be higher and the wavelength will be shorter. Let's watch a video that demonstrates this.
The Doppler effect is the change that you notice in the frequency of a wave when the source of that wave is moving relative to you. For example, imagine that you're sitting by a canal enjoying the lovely British weather when suddenly I appear next to you screaming like a lunatic. From your perspective, it's just really, really weird. However, if theoretically I wasn't standing next to you but was running past you at 80 miles an hour, still screaming just as I was before, as I approach you, the pitch of my scream would be higher, and then as I pass and run away from you, the pitch of my scream would drop. Even though from my perspective, I'm screaming at exactly the same pitch as I was when I was standing still. The reason this shift in pitch happens is because when I'm sitting still and screaming, ah, the sound waves are emitting from my mouth uniformly. But when I start moving, the sound waves in front of me get squished up and the sound waves behind me get stretched out. And it's this change in the frequency that causes the change in pitch as I pass, and that is what the Doppler effect is.